Hi everyone, this is the beginning of our second unit, Logic and Reasoning. So we're going to start with 2.1 Inductive Reasoning. We'll talk about what it is, how it's used in day-to-day life or in math, and we'll talk about some examples. Let's get to it. So inductive reasoning is when you are thinking or reasoning based on observations and patterns. So maybe you're noticing that when you get to school and it's 8:30, it takes you a lot longer to get to the front of the building because of traffic. But if you leave the house a little bit earlier and maybe you're here around 8:15, you realize that there's actually not that much traffic. So realizing those patterns is a scenario, right? You're noticing a pattern about traffic and you're making changes based on these patterns that occur on a daily basis. This other one, you might hear it as an athlete or maybe from your grandmother or someone who has had an injury, right? They can tell when the weather is going to change or when it's going to rain because their joints start to hurt. Maybe their knee aches or their shoulder or something starts to hurt a little bit different. So they're like, oh, it's going to rain. I just know it, right? These aren't facts, but they are conclusions that you're coming about based on these observations that you have. And that's what we call inductive reasoning. So here's an example in math of how you've done or how you would be seeing inductive reasoning, right? In this first scenario, you have a series of 3 pictures and it's shaded, right? And then the thing is like draw/color the next shape appropriately. So if we were to draw this shape, we would have some sort of box. Try not to judge my drawing abilities here. Right? And then we're trying to figure out where it's going to be shaded next. So if you think about it, you start in the left corner, right corner, bottom corner. It starts moving clockwise, right? So the next shaded region that we're going to look at is going to be down here. So we observe a pattern and we form a conclusion from it, right? We try to predict what's going to be next. In the next sequence, we have find the next number, right? What do we notice here? We have 1, 2, 4, 7. If you think about it, from here to here, we're adding 0, and then we're adding 1, and then we're adding 2, and then we're adding 3, right? We're adding an increase of every one every single time, so 7, we're going to do plus 4, and you get 11 as the next number in the sequence. Some of them are obvious or easier to look at. Some of them are a lot more challenging to look at, but the more you practice forming conjectures or forming these ideas, the easier they become. So let's talk about what that is, a conjecture. A conjecture is when you form a rule or a conclusion based on incomplete information. So a really, really good assumption, hypothesis, right? You're trying to form a theory of something that you believe to be true based on what you have. So here, if I wanted to draw the next image, I notice that here we have 1 circle, and then we draw a circle on the outside. So now we have 2 circles. We move over to 3 circles. The next image must then have 4 circles. Right? We have what we start with, the second picture, the next picture, and then finally we have that many. These are supposed to be circles, right? Not so much of a circle here. Let me try that one again, although they're all not very good. So a conjecture is formed when you identify a pattern, right? In inductive reasoning, if you're identifying a pattern or a behavior, they're like, hey, I think this is going to be true every single time. I'm going to keep doing it, and I'm going to be able to continue this pattern by forming a conjecture, okay? So how do we form conjectures? How do we think about it? There's several ways, right? You can think about, am I adding or subtracting something consistently? Is this pattern occurring over time? Am I adding or subtracting? What's changing here? Or it's multiplying or dividing. What's happening here, right? Am I multiplying to get to the next sequence? Am I multiplying by something or dividing by something? When you can think of those 2 rules, it allows you to look at pictures and numbers a little bit differently. It separates things a little bit, and it makes it easier for you to understand what that pattern is happening. The pattern is not as abstract if you see it through the lens of, is this like a sum minus problem, or is it multiplying and dividing problem? So If you look at this first example, how many triangles would there be in the 10th figure? We have figure 1, figure 2, figure 3. If we keep going, right, the 10th figure would have how many triangles? Well, first, let's identify what we got. All right, I count the triangles in the first figure. I notice that there's 4. In the next one, we have 6. In the next figure, we have 8. What's happening every time? What's our pattern, right? Am I adding, subtracting, or am I multiplying and dividing? And if you think about it in this scenario, we're adding 2 every time. So if a situation is not clear to you, ask yourself, is this somewhere where I could add and subtract, or is this something that I can multiply and divide? Right? And then the pattern becomes a little bit more clear, and then you realize that you just got to do plus 2 and keep this flowing until you get to the 10th picture, right? And you're there. And the next scenario is find the number in the next sequence, right? We have 1, 3, 9, 27, 51. Okay, am I adding? Well, let's try it out, right? If you're adding, you can do, we got a plus 2 here. We have plus 6. We have, between these two, plus 18. So notice how you're not really adding something consistently every single time. It's changing. So maybe it's not addition or subtraction. Maybe in this scenario it's, let's see, maybe it's something different. Let's try multiplying. Maybe that works. So what happens if we multiply this times 3? That works. What about times 3? That works too. Okay, I found my pattern. I multiply times 3 every single time, and now I get 53, the next number. So I try it out, honestly. When I look at it, I try addition, subtraction, and then I try multiplying and dividing. And then eventually I'll get to a pattern. Now, if I can't find a pattern through those two, then I might be having to think a little bit harder and into a higher level of thinking. But in this class, we'll be focusing on these two ideas, adding, subtracting, or multiplying and dividing. So, as you're forming these patterns, you're really just forming a generalization. That's really what's happening here. You're forming a rule of what you think is going to be occurring. Now, these rules can be true or they can be false, right? Here we have a few generalizations. Like, if an animal has stripes, then it's a zebra. Or if an animal is a bird, then it can fly. I can think of examples that make it true, but a counterexample is an example that proves it to be false, right? It's an example that you can find that disproves a statement. So maybe when you first think about this example, if an animal has stripes, then it's a zebra, you think it's true. Can you find an example that would prove it to be false? So let's find an animal that has stripes. That is not a zebra. Oh, there's several. You got tigers, cats, you got all kinds of animals that have stripes. Squirrels, right? A lot of them have stripes that are not zebras. So this is going to be a false statement. And my counterexample is, let's go with tiger. I just need to show one example that proves the statement is not true. The next one, if a bird is an animal, then it can fly. Or sorry, if an animal is a bird, then it can fly. Can you disprove that statement? Is it always true? No, this is false. Think about penguins. Penguins are birds and they can't fly. Ostriches are birds and they can't fly. There's different animals that are also are birds but cannot fly. So a counterexample is very powerful because it allows you to negate or contradict a statement. It proves something to be wrong. And when you're arguing with someone, the only way to argue back is by disproving what they just said, by proving them to be wrong. And if they are wrong, then that makes you right. So there's a lot of reasons why counterexamples are powerful, and we'll end with this. But the power of counterexample can help you determine if something is true or false. Okay? If you are given a statement and you cannot find something to disprove it, to contradict it, then the statement must be true. Right? If you can't argue back at something that I've said, because you can't contradict what I'm saying, then you have to accept that I'm right. At the same time, if I am wrong, I don't have to prove all of the reasons why you're wrong. I just have to show you one example why you're wrong. And that one example, the counterexample, can prove that something is false. So you can use counterexamples to prove if something is true or to prove if something is false, depending whether you can find one or not. I hope this has helped and has cleared some things for you. If you have any questions, please comment below, like, and if you haven't subscribed, I don't know what you're waiting for. We'll calculate later.